Welcome to this session. My name is Renee McCormick. I'm the Executive Director of Science Programs for the National Math and Science Initiative, and I'm really glad you're here. This particular recording is to help you through mastering the math of the AP Environmental Science course. Hopefully you are listening to this very early in your journey through the course because these tips, tricks, techniques, whatever you would like to call them, are going to help you navigate the mathematics throughout the course. The free response section of the AP Environmental Science exam is got quite a bit of simple algebraic manipulation math sort of skills in it. And so my job today is to try to help you navigate through some skills, maybe add some skills into your little bag of tricks, your problem solving bag of tricks, I often refer to it as. And let's just get started. The first part of this, of many parts, is dimensional analysis. Now, if you've had a chemistry course, you've done dimensional analysis. It may have been called something else in your course, so you may know it by its other two aliases, shall we say. It's something called the factor label method, maybe what your teacher called it, or a unit cancellation method. But either way, what it means is that it's a quick problem-solving way to convert a quantity that's given, maybe several quantities that are given, into a desired quantity. And the units are your friend. You should not ignore the units. Laziness is not going to pay off here. So the units are what are going to guide you through setting up the problem. The second thing that will guide you is to not neglect the prepositions in a word problem. Those little words, of and at and by. Those things actually help link information together for you. So don't gloss over the little 2 and 3 letter words in the problem thinking they're not meaningful. They're actually the key to linking bits of information together. So let's read through this first problem. Large coal-fired electric power plant produces 12 million kilowatt hours of electricity each day. All right, of electricity is one of those linking prepositions I just talked about. So kilowatt hours is the unit that we use in this country for purchasing our electricity. When your parents pay their power bill, their electric bill each month, they're actually purchasing kilowatt hours of electricity. It'd be interesting for you to go home and ask them. They'd be impressed that you even knew to ask that question. So, and this is per day. So that just linked those two bits together. So that would look like, if I write a conversion factor, it would look like 12 times 10 to the 6 is a scientific notation way, and we'll talk about scientific notation as we go along as well. But I'm too lazy to write out 12 comma 3 zeros comma 3 zeros. It's faster to write 12 times 10 to the 6 kilowatt hours, which is a baby K, a capital W, and a baby H. I don't make these things up. That's just the way it is. Of electricity each day. So then you would write that over day. And we want to also assume in this problem that there is an input of 10,000 BTUs of heat that is required to produce an output of 1 kilowatt of electricity. Lots of ofs in there, lots of prepositions in there. So we just have now a second one of our conversion factors. So we can link 10,000 BTUs of heat energy with 1 kilowatt hour. So the first thing they want us to do is calculate the number of BTUs of heat needed to generate electricity produced by the power plant each day. So it's also useful if you know what your target is. So I mark all over the problem. Students that mark all over the problems at the actual AP exams actually score better than students that don't. This is my personal observation from having scored the AP chemistry exams for many years, which also have a lot of problems within them, like math problem types. All right, so the next thing they want us to do is calculate the number of pounds of coal consumed by the power plant, again, each day. And assuming that 1 pound of coal yields 5,000 BTUs of heat, so 1 pound for every 5,000 BTU. And then calculate the number of pounds of sulfur released by the power plant each day, assuming that the coal contains 1% sulfur by weight. All right, so that doesn't particularly have a conversion factor to it. This is dealing with this idea of getting an answer, shall we say, and then dealing with the fact that the number of pounds of sulfur in the plant each day, assuming that the coal contains 1% of sulfur by weight, because we just calculated number of pounds of coal up in part B. So that brings me to another statement that's going to help you out. You need to let the problem lead you. I actually was on the committee that wrote test questions in the free response section in particular for the AP Chemistry exam. And as a question writer, one of the first things they trained us to do was to write problems that led the student through a logical problem-solving method. So try not to resist being led. I know you're an independent, teenager, but let's try to let the problem lead you. There is a method to the madness. All right, so if you are good with dimensional analysis and you already know what to do, you are more than welcome to fast forward right on past this part. But if you're wondering, scratching your head, I don't even know where to start, then keep listening. We're about to become close friends. So ask yourself, what unit of measure do I need for my answer? That's how you get started. You reread the problem. It's okay to reread the problem 3 or 4 times. Circle things, box things. Come up with a good system that's going to let you be able to glance back up there when you're in a testing situation and pick up the important pieces of information and start to put them together in order to solve what's being asked. So what unit of measure do I need for my answer is what you want to focus on first. So you go back up and you read part A again. And when you read part A again, it's calculate the number of BTUs needed to generate the electricity produced by the power plant each day. So BTUs per day is what you're after. And the word per is code for a divided by. So that BTUs per day in words becomes BTU per day as a conversion factor, as what you need. So a lot of my students preferred to kind of start the problem with the end in mind. So they would actually have done this and started to work backwards to the left. So your next little problem-solving technique is to say, am I given any numbers at all that are paired with the units that I seek? Well, in this one, not exactly, not directly, but you have a couple of different things that are going to get you to your end goal of BTUs per day. It'd be way too easy to just make it a one-step problem. So what you're really looking for is a bridge of sorts, and I put it in quotes because I just couldn't come up with a better word than bridge, that connects BTU and day. So I'm given the fact that the power plant produces 12 million kilowatt hours of electricity each day, so that becomes one of my bridges. And then it introduces, however, something else that I may need to get rid of. So when I read that 12 million kilowatts per day, you can come up with a conversion factor this way, or you can flip it upside down. It doesn't matter which one you use, but you choose wisely to cancel away units that you do not want and get the units that you actually seek, which again are BTU per day. So if I use this one over here, then I get my day down in the denominator where I want it. So I'm going to reject that one for now. And then I also found a bridge of information that was a kilowatt hour for every 10,000 BTUs. Well, what do you think? Look at them for a second. Think about it. I agree. Let's reject this one. Why are we rejecting it? Because it doesn't have BTU in the numerator. So now I've got BTU and I've got day, and I've got the potential to cancel out what I do not want. But kilowatt hours is my bridge between what I do seek. So these conversion factors, like I said, are your friends. Prepositions are also your friends. And you're looking for things that link information together, like pieces of candy or at 15 degrees Fahrenheit. So your objective is to string these conversion factors together, keeping the numbers with the units. Don't get creative and move the numbers around. They've got to stay with their unit. Think of it as your first name and your last name. So we want then to structure our conversion units so that we get rid of, again, the unwanted units, they cancel out, and we are left with the units that we are seeking. In our case, it's BTU per day. So you have probably encountered this before, like I said earlier, 12 inches per foot or 1 foot per 12 inches. We're simply multiplying by a quantity that is the same on the numerator as it is on the denominator. The physical representations are exactly the same. So really this is just a big fat 1. Which is why it's legal to flip them, take the reciprocal, flip them upside down, just because they're representing the same quantity. It's a matter of, are you multiplying by 12 or are you dividing by 12? Which direction are you actually going? All right, so once you've kind of contemplated your conversion factors. You're just going to choose them and you're going to structure them like we just discussed so that I will get rid of kilowatt hours, but I will get BTUs per day. That's what we want. So finally, then the final step is to just solve this sucker. So let's go for it. What do we have going on? Well, we've already figured out that we've got the 12 million kilowatt hours of electricity each day, 10,000 BTUs per kilowatt hour, etc. So I'm again going to start back here wanting each day's worth of BTUs. So BTU per day. So what does that mean? That means I want to choose something that's got BTU on the top. And I didn't get the luxury in the problem itself to be able to just immediately go to day. So I had to look for that bridge. And that bridge was each day kilowatt hours. So then they went on to tell me that we have 10,000 BTUs for each kilowatt hour. So I'm going to go ahead and match the 10,000 with its unit of BTUs. And that went with 1 kilowatt hour. And so I'm hoping to be able to do a direct cancellation here, and I would look back up there at the top of the problem again, and I say, aha, there are 12 million kilowatt hours of electricity each day. So I've got my BTU, I've got my day, I've got to cancel, life is good. Now, you're not going to have a calculator in your hand when you take the AP Environmental Science exam. What? Was that a gasp I just heard? Yeah, I wish I were kidding, but I'm not. You're not going to have a calculator. So you need to learn to expect easy math. And one of the things that you need to get good at is using scientific notation. So I can rewrite 10,000 as 1 times 10 to the 4th. Or if you love all those zeros, you can do this the longhand 3rd grade way. It worked just fine. We'll take the answer any way you want to give it to us. We'd prefer it in scientific notation, but we are happy if you just string all those zeros together. But this simplifies my math. I know you're not thinking that right this minute. I'm going to convince you, hopefully, before we have parted ways on this topic. So 12 times 1 is 12. And then 10 to the 6th times 10 to the 4th is 10 to the 10th. And you're done. And you can leave your answer just like that. Or you can put it in a more classic format of scientific notation, which is often x.xx times 10 to some power. And so if I do it that way, then it would be 1.2. And since I moved the decimal that's understood to be at the end of 12 back 1 space, then I have to multiply by 10 to the 11 because I'm going to move it forward. And it's the point again of not writing all those zeros out. So however you want to turn in the answer, peachy. So 1.2 times 10 to the 11, 12 times 10 to the 10. The folks who score your AP Environmental Science exam, they are both metric literate and scientific notation literate. So you're just going to have to develop your own habits and just not stress about it. They're going to be able to grade your paper correctly. All right, so let's examine part B. What do they want us to calculate? Calculate the number of pounds of coal. I'm going to change colors. The number of pounds of coal consumed by the power plant each day. Assuming that 1 pound, assuming will get you in trouble, assuming that 1 pound of coal yields 5,000 BTUs of heat. They just gave me information to be able to put together a conversion factor, which would look like, they did it in words, but I can do it in math, 1 pound of coal for every 5,000 BTU, or I can flip that upside down if that better suits my problem-solving purpose. All right, so again, I kind of like to start with the end game. Until you get the hang of this, I think it really is easier to look at the units on the answer and work your way backward to structure your conversion factors to achieve that answer. So I'm looking for pounds of coal. So it's this conversion factor I'm not going to flip upside down, just this purple one I just wrote, because I've already got pounds of coal at the top. So this is a good thing. So we'll just put it into where I want it in my problem. And now what else do I know? Oh, part A. Yep. Let the problem lead you. The test writers are instructed to write questions that lead the student through a logical, mathematical, problem-solving progression. Fancy ways to say let the problem lead you. So take your answer from up top. So I'm going with my 1.2 times 10 to the 11 BTU per day. All right, so now the bad news. You don't have a calculator. I know, put it down. Put it down. You don't get to use a calculator on the APES exam. If you use that calculator to do everything all year long, you are not going to develop your problem-solving prowess. So you need to just accept now that you're going to be doing an awful lot of arithmetic. So you got to figure out how you want to do this. I can take 1.2 and divide it by 5 if I write this as 5 times 10 to the third, but you got to figure out how your brain does the math best. You may want to do it longhand with all the zeros involved, like 4th grade long division. But it's up to you, but you're going to have to figure out what works for you. So I'm going to go with leaving this as 12. Actually, I'm going to make it 120 because I'm thinking 5 goes into 120 without a decimal point to mess me up, more so than any other way I could structure this. But you got to figure out what your brain does. So if I make this 120, it's going to be times 10 to the 9 zeros. Because there's my 1.2, I went, that makes this 2 less decimal places if I make this number up here, 120. So that's what I'm going to do to attack it. And I'm going to write this as 5 times 10 to the third. So now what I'm going to do is take my, off here on the side, my 120 and divide 5 into it. It goes twice, 10, 20, 4. Then I'll deal with these exponents. Oh wait, these exponents are easy to deal with. So right now I've got an answer that is going to be, it's not how I'm going to report it when I'm all done. This is my scratch work. It's going to be 24 times 10 to the, and I'm asking myself what? Times 10 to the what? Well, when I wrote this as 120 times 10 to the 9, and I wrote this as 5 times 10 to the 3, then all I have left to do is deal with the fact I've got 10 to the 9 and 10 to the 3, where 10 to the 3 is being divided into 10 to the 9. Well, the cool thing about it is with these exponents, you just subtract. They're both by the same power of 10, so this becomes 24 times 10 to the 9 minus 3. So what does that end up being? 24 times 10 to the 6 pounds of coal, and I'm done. Or if you like, you can make it in the standard scientific notation, 2.4 times 10 to the 7 pounds of coal. These are both correct answers. Both of them would bring a smile to my face if I saw them on your paper. Now, calculate the number of pounds of sulfur released. Okay. Pounds of sulfur released by the power plant each day, assuming that the coal contains 1% sulfur by weight. What did they just have us solve for? Let the problem lead you. We just solved for pounds of coal. So I'm going to take that and I'm going to use it over here. But what am I ultimately going to answer in? What are my units for that answer? Pounds of sulfur. So pounds of sulfur is what I need to end up with on the top. So I'm going to start again with my big giant quantity of coal in pounds, which is 24 million, 24 times 10 to the 6. You can put it all out in scientific notation. You can do it in numbers. It's completely up to you. So to humor you, this time I'll do it in numbers, just to kind of show you that it doesn't really matter which way we do it. So now I have 24 million. That's 24 times 10 to the 6. That's also 2.4 times 10 to the 7. 1, 2, 3, 4, 5, 6, 7. Yep. Pounds of coal per day, assuming that the coal contains 1% of sulfur. Well, there's a couple of different ways you can do that. You can say I have 1 pound, because 1% per cent means per 100. How many cents are in a dollar? Those are pennies. Yep, 100 of them. How many years are in a century? 100. So when I do percent, if it's 1%, it's 1 per 100. So 1 pound of sulfur, I'm going to use the chemical symbol for sulfur, which is S, over 100 pounds of coal. Coal's a mixture, so it doesn't have a slick chemical symbol. And so what does that mean? That means I'm going to knock off 2 of those zeros is what that means. When you divide by 100, you just knock 2 zeros off. So I get 4 zeros, and then 240,000 pounds of sulfur. If you prefer it in scientific notation, 2.4 times 10 to the 1, 2, 3, 4, 5 pounds of sulfur per day. Either way, we'll take it. But do not leave the number naked. You must put the units. The units are your friend. The units are worth points. So how would this be scored? Well, if you got the problem set up correctly, but you made an arithmetic error somewhere, like you didn't move a decimal properly or something like that, you're still going to get 1 of the 2 points for each of these parts. This is not difficult math. It's really not. It's Are You Smarter Than a Fifth Grader Jeff Foxworthy level math. If you don't know what that means, Google it. You might get a little chuckle out of Jeff Foxworthy. So you need to relax about it, and you need to realize that the work is worth a point and the final answer is worth a point. So if you mess up the final answer, you could still get a point if you had your problem structured correctly on paper. Notice that I box my answers. I am begging you to box your answers. As being one of the people that has scored the AP exams before, I look at the box first, and that's how I award credit. And then I work backwards to see if you did the work that matches what's in the box. In other words, you didn't just look on somebody else's paper. So when you box your answer, it makes it a lot easier on the people who score your paper. And you want the people who score your paper to be happy. You want them to like you. So write neatly, write big, because the people who score your paper are, well, old, like me, and our eyesight is failing. So help us out a little bit. Write big, write neatly, and box your answers. All right, so let's work through this second problem. Environmental impact of washing a load of dirty dishes in an electric dishwasher differs from that of washing them in a sink by hand. A comparison of the 2 methods may allow consumers to spend their money more wisely. Use the assumptions in the table below to perform calculations that follow. Be happy when you see this table, because the table kind of helps you sort out and gives you a spot to write a lot of the different conversion factors or important mathematically related bits of information that you're going to need to solve parts A, B, and C. So all the dishes fit into a single load. Nice to know. The water entering both the water heater and the sink is at 50 degrees Fahrenheit. So you know that you have to wash dishes in warm water. So we'll call that an initial temperature. And then the water heater and the dishwasher are both 100% efficient. So nothing like multiplying by 0.9 because the dishwasher is only 90% efficient, or the teenager washing the dishes is only 70% efficient. You'd multiply by 0.7 at the end. Don't have to worry about that. Both are 100% efficient. So washing the dishes by hand requires 20 gallons of water. So hand, 20 gallons of water, heated to 110. Well, the difference between 110 and 50 is 60. So the change in the temperature for the dishwashing by hand, I'll use H for hand, is going to be equal to 60 degrees Fahrenheit. I can feel it coming on that I'm going to need that piece of information. Work enough problems, you do get some instincts about them. All right, and then in one complete cycle, the electric dishwasher uses 10 gallons of water heated to 140. Less water, but more heat. Maybe offsetting events. Who knows? So the delta T for the dishwasher, put DW for dishwasher, is the difference between 50 and 140, which is almost 100 degrees, but just shy of it, so it's 90 degrees Fahrenheit difference. And the dishwasher also uses a 0.5 kilowatt hour of electrical energy for its mechanical operations, all that noise it makes. All right, so now I think I'm ready to actually figure out what they want me to do. British thermal unit, or BTUs, the amount of energy needed to raise the temperature of 1 pound of water 1 degree Fahrenheit. Additionally, 1 gallon of water has a mass of 8 pounds. So they just gave me some good conversion factor fodder there. And then calculate the total energy used to wash a load of dishes using the dishwasher. So I'm talking dishwasher here. So I take my 90-degree temperature change and kind of get started with that. Or you can do it the way we had been working the others if you prefer. This is the good time for you to decide what you like better. I'm going to end up with an answer in energy per load, so BTU per load. So you may want to work from the backside of the problem. If you do it that way, then what are you going to want to get rid of first is kind of what you have to ask yourself, or what do you want to introduce first? So if I'm going to work from the back end, I'm going to go with the BTU business. That 1 BTU is going to be 1 pound of water, 1 degree Fahrenheit. Okay, I've already made progress. My degrees Fahrenheit are now out of my life. Now, if I could get pounds of water out of my life, that would be even better. So how am I going to get that out of my life? Well, let's see. I've got 8 pounds of water, so I'm going to put that on the top so I can get rid of that pound of water in the denominator. Over 1 gallon. Okay, so pounds of water out of there. I got BTU. Now I just need gallons per load. And I am home free. So how many gallons per load did the dishwasher need? Did it need 10? Washing by hand required 20. This needed 10. So 10 gallons for each one load. And now gallons are gone. And I have only BTU per load. Now, did you see what I just did? I didn't worry about the numbers at all. If I don't have the units all canceled out and the correct unit on top and the correct unit on bottom, numerator denominator moment, there's no point in doing the math. Now, you don't have a calculator, so you're going to have to crunch some of these numbers by hand. So you got to figure out how you like to do that. So now that I have this all set up properly, let's actually crunch the numbers. It's worth it at this point. But you had to see what I was doing. I wanted to make sure that all the units were in the right place and they were all canceled out so that I would get my BTUs per load. So 9 times 10 is 900, and that times 8, 9 times 8 is 72, and I've got 2 zeros after it. So I have 7,200, and that's it because everything else is a 1 along the bottom. That was kind. So 7,200 BTUs per load. So now we're going to do the same thing, same song, second verse, but we're going to do it for this, the load of dishes by hand. So the temperature change was different, wasn't it? Yes, the temperature change, because you're going to want to put your hands in 140 degree Fahrenheit water. 110 is hot enough. So it's 60 degrees temperature. I don't have to think about this twice. I just do exactly what I did last time. 20. 20 gallons by hand. Took twice as much water, right? 20 gallons of water by hand for each load. There's still 8 pounds. That didn't come out very pretty, did it? 8 pounds of water per gallon. 1 BTU for a pound of water, increased by 1 degree Fahrenheit, and degrees Fahrenheit cancel, pounds of water cancels, gallon cancels, BTU per load. Once again, if that doesn't work out, there's no point in doing the math. So now what do I have? Well, I've got 6 times 8 is what I focus on right here. 6 times 8 is 48, and then 48 twice is 96. And then how many zeros? 1 there and 1 there. So 9,600. You do your arithmetic however you like. I am lazy. If I can do it in my head, I'm going to do it in my head. If I have to use all my fingers and toes, I'm going to use all my fingers and toes. My last resort is to actually write something down. So I come out with 9,600 BTU per load. So now what? Finally, in Part C, calculate the cost of electricity for each dishwashing method, given that 1 kilowatt hour is equivalent to 3,400 BTUs and the cost of electricity is 11 cents per kilowatt hour. You are going to have to reach for a calculator on this one. This is not as friendly a math as what we've had before. So let's look at what we did first in green up here, which is what went with the dishwasher. Okay, so dishwasher. What did we have? We had 7,200 BTU per load. And I want to get rid of BTU. And I want to get kilowatt hours because they gave me that piece of information right here. So 3,400 BTUs for each kilowatt hour. So that's out of my life. And I want cost of electricity. So somewhere I need to get a kilowatt hour out of my life. I need some money. Well, they told me it was 11 cents. So there's my dollar. And you may prefer the dollar in front of the 11. That's how I'm used to writing it. But it works either way. Per 1 kilowatt hour. So that's going to get rid of my kilowatt hours. And that's going to get me a cost per load, which is what they're asking me to do. All right. So I can't do this math in my head, so I'm actually grabbing for a calculator. This is what happens sometimes when you pull problems from different sources. But on the real exam, I remind you the math will be easy enough that you won't have to grab a calculator. Okay, so I took the 7,200 and divided it by the 3,400, and now I'm going to multiply that by 11 cents, by 0.11, and I come out with 0.23. So what is that? Really, that's 23 cents to work that load of dishes. In terms of electricity, that does not count the price of the water. They left that out of this problem. But hey, it's complicated enough. Aren't you happy? Say a prayer of thanks. Okay, and then sink. Same song, second verse. Only we had 9,600 BTU per load. There's still 1 kilowatt hour for 3,400 BTU. And the cost is still times 0.11 gives me a value of 31 cents. So it is a little more expensive in terms of the cost of electricity for the dishwashing method to actually wash them by hand. Interesting, huh? But again, I say, remember that does not include the price of water. All right, moving on to part 2, determining energy efficiency. All right, with energy efficiency or any sort of efficiency, it's a what did you get out of what you put in? It's that ratio of how much work was it that I had to put into this and what did I get out of it. Nothing's 100% efficient ever. Because you always lose in these energy transfers. You lose some energy due to friction when you're transferring, let's say like with our dishwasher, mechanical energy, heat energy. When you're making those transitions, you're always going to lose some of the energy due to friction. Friction of the molecules, friction of the moving parts. You decide, there's lots of friction. All right, so energy efficiency, simply that ratio of work output to work input. If the problem says that a system is less than 100% efficient, then the energy output has to be divided by the efficiency to determine how much energy input is needed. So our previous example made this really easy on us because they told us it was 100% efficient. But don't always expect that because such, like I just said, such machines do not exist. If a machine or a process is 75% efficient, you just assume it's 100% efficient while you're working the first part of the problem, but just don't forget to multiply by that efficiency percent in decimal form. So you got to reduce the number because if it's less than 100% efficient, you're not going to get all that fabulous energy that you just, or work that you just calculated out of it. All right, since that was probably about as clear as mud, let's look at a problem. Answer the questions below regarding the heating of a house in the Midwestern United States. Use the assumptions in the table below to perform the calculations that follow. So the house has 2,000 square feet of living space. Good to know. 80,000 BTUs of heat per square foot are required to heat the house for the winter. Okay, so that looks like 80,000 BTU per square foot, foot squared. Natural gas is available at a cost of $5 per 1,000 cubic feet. That looks like this. Oh, per 1,000 cubic feet. And no, a foot cubed and a foot squared are not going to cancel each other out. You can cancel the square part completely away, but it'd leave you with a foot. So we're either going to have to get rid of square feet and get cubic feet, or some trickery is going to happen here to get us so that those end up being the unit that we desire. So 1 cubic foot of, there's our way to get rid of it. 1 cubic foot of natural gas supplies 1,000 BTUs of heat energy. So 1 cubic foot of natural gas supplies 1,000 BTU. Keep running right. BTU of heat energy. The furnace in the house is 80% efficient. Oh, there's the twist. You can't forget about that part, because we're going to calculate it as if it's 100% efficient, and then we have to realize that we got to multiply by 0.8 at the end, or divide by 0.8 depending on what it is they've actually asked us. So it's either going to cost us more, that's when we would divide by 0.8 to inflate our dollar value, or the other way around. All right, so what are we going to start with here? Read the problem. Calculate the number of cubic feet of natural gas required to heat the house for 1 winter. Show all the steps of your calculations, including units. All right, so how big is this house? 2,000 square feet. Now, ideally, I would like to get rid of square feet. So, can I? Yes. How can I? Because they told us there are 80,000 BTU per square foot. So, part of my mission is accomplished. Then what? Now I need to get rid of BTU. Can I do that? Yes, I can, because I was told there's 1,000 BTUs for 1 square foot of gas, 1 cubic foot of gas, cubic foot. I didn't put my cube on there. So 1 cubic foot. All right, so now I've got to calculate the cubic feet of natural gas. I'm good. What else do I need to know? I think that's it. Yes, I don't need this one. All right, so foot cubed, cubic feet, everything else is canceled out. Life is good so far. All right, so what am I going to do with all these numbers? Let's think about them as 2 times 10 to the third, 8 times 10 to the fourth, 3 zeros, 4 zeros, 1 times 10 to the third. And my math just got a whole lot easier. So 2 times 8 is 16, times 1 is 16. So my numerator is 16, my denominator is 1, so that comes out to be 16. But let's deal with the fact that I've got 10 to the third times 10 to the fourth, which is 10 to the seventh, over 10 to the third. So that simplifies to 16 times 10 to the fourth, also known as 1.6 times 10 to the fifth, foot cubed. Foot cubed. Either one of these is okay. I'm going to go with that one. But it's equally correct to have written it as 16 times 10 to the fourth. But wait. Calculate the number of cubic feet of natural gas required to heat the house for 1 winter would be if this were 100% efficient, but it isn't. So I need to take that number, the 1.6 times 10 to the fifth, foot cubed, and divide it by 0.8. Oh, if you prefer. I got to get that 80% efficient business in there. So, again, why is that happening? Because isn't it going to require me to buy more cubic feet of natural gas, since there's obviously some leakage or something that's keeping it from being a 100% efficient process? So If I multiplied by 0.8, it would come up with an answer of less natural gas required to heat the house. That can't be right, so I'm going to have to divide. So if you get stuck, just grapple with the common sense. All right, so what does that look like? That looks like 1.6 over 0.8 times 10 to the fifth, which is also known as 2. So 2 times 10 to the fifth cubic foot. So I disagree with that. 1.6, with that waste that's happening to keep this down to an 80% efficient, is going to really make me have to buy 2 times 10 to the fifth cubic feet of natural gas, also known as 200,000 cubic feet. So there is my correct answer. So when you get into that efficiency thing, you have to go, but wait, I calculated it as if it's 100% efficient, and I just divide by how inefficient it is in decimal form. All right, so now finally calculate the cost of heating the house for one winter. Well, we just said I have to buy this much cubic feet of natural gas to heat it, and then some kind of conversion factor to get rid of the cubic feet. So come back up and peruse your table. What is going to work for you here? It was $5 per 1,000. That's 10 to the third. So that's written over and understood 1. So what is 2 times 5? That's $10 times 10 to the 5 minus 3. I know, you're going, hey, that's 2. I agree with you. 10 times 10 to the second. This is in dollars, because my cubic feet canceled out, so the only thing left here is dollars. So 10 times 10 to the second is also known as $1,000. 10 to the third, if you prefer. But when you talk money, very few people write it in scientific notation. They do, however, go to like 5.2 billion or 6.3 million when you're, talking about exorbitant costs, shall we say. So I'm going to stop here. We've got another part to this, which is going to be the scientific notation and such. I hope you have a great rest of your day.